Welcome to this last PASC21 session. So today we will have first keynote speaker, and then we will do the formal closing. So today it's my great pleasure to welcome Geronimo Castrillon. So Geronimo is professor in computer science at the Technical University Dresden. He's a chair of the computer construction with a focus on new tools, language, algorithms, and programming. And I think we will hear here interesting contribution and important contribution from the computer science community towards the scientific computing community. And I think it's one of the few keynote speak at PASC where we will have a computer science centric talk, and I think that that's very interesting and welcome. So the title of Geronimo's talk is Domain-Specific Language to Tame Heterogeneous and Emerging Computing System, and we will learn how to face the difficulties to program and use heterogeneous computer, how to democratize high-performance computing, and see whether this domain-specific language are a possible avenue to solve this problem. And Geronimo will illustrate this with example. So Geronimo, you can, the floor is yours. I'll let you share your screen and come in front.
Great. So I hope you can hear me and you can see my slides. So thank you, Bastien, for the nice introduction, and thank you in general to the PASC organization for having me here. So I think it's a huge burden to be the computer science keynote speaker, the first one. Yeah, so at this point, I guess I will also give some advertising to a session that I just visited. It was a session, a mini symposium on DSLs for climate modeling. So I think it was very interesting. So if you want to go into the details, you should maybe watch the videos of that session. So yeah, so I'm Geronimo. I'm going to be talking about DSLs to tame these heterogeneous systems that are coming into computing systems soon. So let me just jump into an introduction. And I think this is something that most of you have seen, right? You have Moore's law on one side, and you have this era of diminishing returns where we started going multi-cores. And so this evolution continues. And I like to talk about this evolution as having these inflection points, right? So in the mid-2000s, we started getting multi-cores. Then at some point, we couldn't power all the cores at the same time. And today we hear a lot of fancy technologies like quantum computing, you have heard of, but also carbon nanotubes, organic electronics. So there are many alternative technologies that have been proposed or that are being proposed to advance the computing roadmap, right? So yes, examples are massive parallel and heterogeneous systems. You have specialization in the forms of TPUs or AI engines in Xilinx, FPGAs. You have phase change memories as accelerators. You also have new emerging non-volatile technologies for memories, and you have new interconnections, right, like silicon photonics and new technologies for wireless connection within computer racks. So I think there's a lot of heterogeneity here, and I brought some pictures, right, going from what we have today, right, AI accelerators, to something that has been prototyped at Stanford. This is the next like 3D stacked architecture, very fancy machine with carbon nanotubes, and all the way to very exotic accelerators. So the one on the bottom is something that is being developed at Max Planck Institute in Dresden, where they work with microfluidic chips and proteins actually to do computing. So there's a lot of very interesting things that are being proposed, and some of these things are going to make it in our systems, making this heterogeneity really, really complex, right? So I guess we all agree on that, and we also agree that that's a huge problem because we have very pressing things like weather, climate modeling, physics of any kind. So many of the things that you guys are experts in, right, in scientific computing, really depend on how to leverage the computing power of these machines, right? And it was very difficult already in the 2005 when I started actually doing my PhD, working on auto-parallelizing compilers and so on. It was already quite difficult back then to be able to deal with those architectures. Then it was more difficult with traditional heterogeneity, right, with GPUs. It's going to be more hard moving forward. So we have experts, right, domain experts that are just yelling at frustration to the machines, right? Okay, so what motivates the research that I do in part is this idea that this golden era in computer architecture, which is a term that has been coined recently, right? Because you have all this proliferation of new ideas, requires major challenges in programming methods and programming abstractions and programming tools, so that we can actually democratize the system so that everybody can use them, right? Not only the experts, right, like the ninja programmers or the people that understand the technology. And I think this is a trend that you have seen over the years, right? Moving through GPUs, through tensor processing units, through FPGAs, and I think this is just going to increase. Okay, so let's look at why do I think we need new languages or new abstractions. So this is an example of something that we want to write, right? This is a mathematical expression, and you guys in the scientific computing community would know what that is, right? And we can go on and write that naively into C code. So this is actually C code implementing that expression. And the problem is once you give that to the compiler, this is what the compiler sees, right? And this is already simplified, right? I asked a PhD student of mine to give me a simplified version of the LLVMIR, like the compiler representation of the piece of code. And so this is what it sees. So I guess you see that there's some complexities. For us, it's way easier to reason about this expression, right? It's easier to just move things around than it will be to move things around in this graph. We have to do a lot of checks to be sure that we are doing things right. So what we're doing here is kind of a generalization of matrix vector multiplication. These are just tensor operations here. And so back maybe 10 years ago, I was very excited by research by Markus Büchel, whom some of you may know, right? He was asking already back then, 10 years ago, how often do we have to optimize by hand matrix vector, matrix multiplications, FFT, and so on and so forth. And that's kind of what motivates some of the research that I do on languages and compilers for existing and emerging systems. So, okay, so what can we do? I mean, if we stick to C code, there's still some hope, right? There are people working on compilers, like low-level compilers to understand patterns in C code. So there is a little bit of hope for some regular loops. And here, the keyword here is polyhedral compilation. That's also a domain in which I do some work. And this is a plot that is not from my group. And what you see in this plot is that if you take just the C code implementation of a tensor operation, right? So you would get a performance gap, which is quite huge, right? So this is using normal polyhedral methods. This is using Clang. The Intel compiler is a bit better, but still there is a gap to Intel NKL if you use libraries, right? So what they did is that they developed a method in which they can recognize patterns. So they can reconstruct from the very complex graph that I showed you before. They can reconstruct, okay, this is a tensor contraction. Now that we know that it is a tensor contraction, we can do very fancy optimizations and almost reduce the gap to optimize libraries, right? So there's a lot of important work being done in this domain, but this pattern recognition is complex. So it's also very sensitive to coding style. So that's why this is important work to address legacy code issues, but it's not the solution for everything. And so as this pattern recognition, there are other stuff like polyhedral compilers I mentioned, trace-driven dynamic parallelization, and these patterns are more complex idiomatic extractions. Like for example, this one over here. So this is also not from my group. What you see here is a very typical code that we write to walk through a data structure, right? So we're walking through a graph and we're calling a function f on the node. The rest of the code is just bookkeeping, right? Have I visited the node? Have I not? And so on and so forth. So if you give this code to a compiler, it's really, really very difficult to expect the compiler to identify that this is actually a very data level parallel computation. So it's people working on how to do that. And so I think that's a very valuable thing that the point is that there's only so much that we can reconstruct using this kind of pattern-based methods. So that's where this mountain that I stole from a paper recently published in CGO, and also is an analogy that has been used by Paul Kelly and Imperial College. What you see here is that we want to have a high level of abstraction, and by recognizing these patterns, you could kind of go and do progressive raisings. You can raise the level of abstraction, and here the analogy is that the higher the abstraction, the more potential you have to get speed down the slope, right? So meaning that you can get better performance. And so that's kind of the motivation by recognizing these patterns, understanding, okay, this is a tensor contraction, so let's deal with that as a tensor contraction and find better ways of optimizing this code. I've also heard that, yeah, so the higher you go, the more likely it is that you cause an avalanche. So that's also maybe part of the game here with DSLs. So right, so with DSLs, we want to start up there. So we want to not reconstruct patterns, but we want to express the patterns with a matching abstraction. So in that sense, we want to kind of bridge the gap between domain experts, maybe not the Ninja C++ programmer or the Fortran programmer, and languages like C++ or Fortran. And just to mention a few DSLs, so there are already very successful DSLs for performance, and so we are concerned here with performance, not a DSL just for productivity, but for performance, for portability, and so on and so forth, as I have heard in this conference already. And so languages like Halide, Spiral, TVM, TensorFlow, FireDrake, those are examples of languages that have been very successful in optimizing complex codes. So what I'm going to do in the next couple of slides is I'm just going to give you 3 examples of DSLs that we have been working on in my lab. So granted, these are still academic examples. So these are, we just interested in the principles and see what we can do with those principles. Can we optimize? Can we match the performance obtained by people actually coding for performance? And later on, I'm gonna kind of bridge the gap into emerging technologies and how these DSLs are helping us generate code for systems that are maybe not even von Neumann, right? Okay, so let's start with the first one. So the first one is one that, so this use case, I guess, is very common to some of the people in the audience. What you see here is, again, this expression from before now expressed as a tensor operator. So you have a matrix with the tensor auto product, and this is multiplied by the element. So this is actually a use case that we developed in collaboration with people doing CFD, spectral element methods for CFD. And of course, we were using tensors. So in machine learning, we also use tensors. So we also found some applications of this tensor language for machine learning. And so this is the mathematical expression. And so right now, we kind of have 2 different syntaxes. So one syntax, and this is implementing a slightly different kernel, right? This with 3 different matrices. So this is syntax just based on C++ template metaprogramming. So here you don't have to leave the C++ world. You can still express the tensor in an easy way. And this is actually the first syntax that we propose. This is just plain text syntax. And the reason why we provided this syntax is because this was embedded in a huge simulation for CFD. And so what they actually did is that they wrote this thing as plain text. So in their Fortran code, they inserted this string, and they could pass this string to our compiler. And so our compiler would produce the code and generate a function that they could call. So that's how we did that very poor integration, so to speak. Okay, so what can we achieve? So I showed you this thing before. I showed you the simple C code that implements the same thing. And now this is the DSLs. And so I think we can agree that this one is a little bit better than that one, a bit easier to read. And the one that you see on the right is actually very close to the implementation that experts would code. And this is actually code that is generated by our compiler. And the difference in performance between these 2 codes is of 100x. So it's actually a very, very huge difference. And that's why I said that this is very naive code. This is really if you have no idea about what you're doing, right? You take this and you just implement those additions all together, right? And if you do a bit better with OpenMP and vectorization, you can improve performance quite a lot. Okay, so how do we do this? How can our compiler from this expression generate code that looks like this? Actually, there is not a lot of magic there. First, we can leverage algebraic identities. So we know things like associativity and distributivity, these kind of things we can leverage. And we also can leverage expert knowledge, right? So we know what people do to optimize for this kind of codes. And now we can kind of generalize those heuristics that people have been using to different architectures. And in that way, from a very simple expression in our DSL, we can generate a huge amount of variance. So these are actual compiler graphs, like similar to the compiler graph that I showed you before. These are actually compiler graphs that implement the same functionality, okay? And the point that I want to make with this figure is not that we don't have to understand the graphs, of course, but it's very easy to generate these different implementations from a source in a DSL. But you can imagine that it's very hard. Like, for instance, if the programmer gives you this graph, imagine how many steps do you have to do, how many analysis do you have to perform to be able to transform that graph into something like this. So some of these graphs are look very different to each other, right? And so that's kind of the point of the value of the DSL, right? Starting from above, it's easier to generate different variants. What do we achieve with this? So actually, so these are some plots of performance, right? So gigaflops here, also there for two different kernels, interpolation and inverse Helmholtz. And this is a spectral linear method. So we're using some polynomial degrees here. So for different polynomial degrees, kind of the difficulty of the program increases. And what you see here is these two ones are using libraries like dgem. And you see that people in this, so our collaborators working with Fortran, they had a optimized version, which is the blue one. And you see that the optimized version is already better than the one implemented with libraries. And they used to just port that to different architectures. And what you see now in green and red, those are versions generated by our compiler. And so this is actually very interesting. We were able to match the performance of the manual code, often improve over that performance. And also what you see here is that different variants, like the red and the green, sometimes the one is better than the other, right? So it's not which just showing us that it's not a trivial optimization problem, right? You have to know things about the architecture. You have to know things about the particular polynomial degree to select the best performing option. Okay, so let me move a little bit faster through the next slides on this tensor languages. So what we went on and did is that we added more general operators with tensors, and also we added metaprogramming. So now there is also a role here for the compiler expert. So you have somebody writing the code for the operator, and then you have somebody maybe accessing the internals of the compiler through metaprogramming. And so now we have formalized some transformation primitives, like things that you may know, like interchange to interchange loops. And based on these basic primitives, we can compose a bunch of transformation primitives to achieve something that you may be familiar with, for instance, styling, right? And now we have a language in which you can define the computation and then have an AST, and then somebody expert in performance can, at this high level, manipulate the AST with these transformations. And these transformations are all formally defined and through this denotational semantic that is being shown here in the slide. So what do we achieve with this one? So here are some plots. Now it's not only interpolation and Helmholtz, but we have other benchmarks common for the domain, right? And what you see in some of these plots is that sometimes, so our solution is the red one. Sometimes we're actually better than Pluto. So Pluto is the state-of-the-art polyhedral compiler that should be doing very well in this kind of codes. And sometimes we can do better. And the reason we can do better is because we have these high-level semantics. We can do transformations in, like for instance, transpositions and so on that are that the Pluto compiler simply cannot do. In some other cases, like for instance here or there, you see that the Pluto compiler was produced a solution that was faster than ours. And here we went and checked what the Pluto compiler did, and we actually could reproduce the exact same computations or the exact same optimizations through our metaprogramming approach, right? So it's not a question about expressivity. So we can still reach those variants. So we're not losing those variants. It's just that for the plot in this paper, our optimizer was just doing some simple heuristic. So the problem of finding the most profitable transformation, that's still a huge problem, but is one for which we're working on different heuristics, including machine learning. And the final slide on the tensor language, so this was the first example that I want to show to you, is that now that we have formalized these different tensors, and we looked also through different tensor languages, like for instance, the TACO language from MIT, or the language in TVM for machine learning, and we extracted a core intermediate language that describes some of the operators that are used throughout these frameworks. And we actually formalized with operational semantics how this language works. And so we came up with a intermediate language for tensors that is provably, so that you can prove that there's never going to be an out-of-bound access. So you're not going to get segmentation faults and this kind of stuff. And I think that's a very important added value of formal languages that you can get with DSLs, because DSLs are simpler. So you can do verifications. You can do some tasks that are difficult to do in mainstream programming languages. And just to what I'm showing here at the top is a code snippet from TVM, I think, that was in an example. And this code snippet had actually an error, right? So the way the matrices were accessed was incorrect. And this can be caught by a type system as shown in this paper. Okay, second example. This one will go a bit faster. I'll check how I'm doing in time. So this is an example for particle mesh simulation. So this is also in collaboration with people doing, in this case, computational biology and this kind of simulations. And so they are working with particles and meshes. So particles, because they can model discrete, continuous, deterministic, and stochastic kind of phenomena. And so we have a syntax that looks very close to the mathematical expression. So this would be the syntax for a continuous problem. So you can write the differential equations. So this syntax, of course, has been beautified. But in principle, you will be writing the differential equations very similar to what you see here. And this would be a simulation for particle-based, so where you have a simulation where particles represent discrete things. And so here you see that in the language, there is some syntax for interaction and evolve, which is kind of the like the two basic operators that we use in particles. And from this representation, we can do, for instance, things like automatically interpolate from the particle representation into the mesh and back and forth and so on. So this is kind of the syntax that we come up with working with computational biologists. Below this DSL, there is a library which is called OpenFPM. So actually, the library is doing the heavy lifting in terms of distributed computing. This is a library that was recently published from the group at Max Planck Institute for Cell Biology and Genetics. So it handles CPU, GPU transparently, supports dynamic load balancing and everything that you would wish from a library like this. And so here as well, we have like we had between C++ or Fortran and our DSL. Here you also have kind of a semantic gap. So this is, for instance, an operation that you want to write. If you write this in the library, you get code that looks like this. And this is already quite abstracted. So the library is already providing a lot of abstraction through template metaprogramming. But I guess we can all agree that this is very complex. So this is a 3D problem. So that's why you have kind of code replication. And so I guess we can all agree that it's difficult or it's easy to make a mistake, right? If you here in the C dimension, you put X or Y. So it's easy to insert some copy-paste errors here. And that's kind of the things that we wanted to avoid with a DSL. So here, as we do with DSLs, we defined a kind of a model for what we want to export with syntax and semantics, right? Like, what do we want to offer to the programmer? And from this model, we can then offer different syntaxes. So this is a syntax that we for instance have for the vortex thing that you saw before. And actually, this is actual code that was written in the library for the vortex simulation that I showed an image for. Right, and now we have our intermediate representation, and from this intermediate representation, we can then generate the library code. And so what I want to highlight here is that this is a model-to-model generation. So there is a model for the DSL, there is a model for the OpenFPM C++ version. And what that means is that so when we produce C++ code, we are, so far, if we made the model correct, then the C++ code will actually compile and run. So there shouldn't be an issue, there shouldn't be any error in generating C++ code. And that I think that is something that when we do DSLs, we sometimes neglect, right? We take the DSL, we generate just text. And so you can imagine how frustrating that could be if you write something in the DSL and then you get an error from the C++ compiler and an error from template metaprogramming. And those errors are really nasty and ugly to debug, right? So I think this correct by construction is an important aspect that I want to highlight here. So in terms of results, where are we with this prototype? So we can run things like Lennard-Jones, Gray-Scott, and Vortex in Cell. And the reason I'm showing these three is because these are different kinds of simulation, right? This is particles and discrete particles. This is mesh, continuous problem. This is hybrid and continuous. So here we're moving between meshes and particles. Here you see the comparison in terms of lines of code. That is not a very good metric, but we have to live with that metric. So we use less lines of code, and I think you should also take into account that the lines of code here are C++ lines of code that are just by all the template parameters that you have to send way more complex than the lines that you would have here. And here this is just a performance in execution time using the code that we started with from the OpenFPM implementation and the one that we can generate from the DSL. And you see that in these two cases, we're more or less on par with the library implementation, sometimes a bit faster even. In the middle, we are not doing very well. We know why that is. So we generate code for the meshes always separately. So we just have to do some loop fusion to merge those mesh computations, and then we would just get to it. Good. So what are we working on right now for this on this prototype language? We are interested, and we already do this. So we insert the Gauss gets and Gauss puts automatically based on high-level data flow. And we have been working on model-based auto-tuning for discretization. And this is something that I think is quite interesting. So in the DSL, we can annotate what kind of method we want to use, right? DSE or SPH are some methods, right? You see them here. And so there are some known error bounds when you're working with these methods, right? So you know more or less what is the curve of accuracy that you wanna follow. So we actually use those curves to do auto-tuning to tune the parameters. And so a paper hopefully will come out with a description of what we did here. And so these are some results for Gray Scott. So we have results for the other simulations as well. And what you see here is that so this is ours. This is our auto-tuner. This is the time of the best simulation that the auto-tuner could obtain. And so you see that if you use other heuristics, so these heuristics here are oblivious. So these are just general auto-tuning heuristics that you see in auto-tuning frameworks. So they could be a couple of orders of magnitude slower. And so if we allow those heuristics, like for instance, genetic algorithms or simulated annealing, to run for longer time, they can really match the performance that you get in this auto-tuning. So I think this is very promising. We have the information from the DSL. We know what discretization method we're using. So we can actually help tune some of the parameters for the discretization approach. And this is something that we actually tested with programmers and have them compete against the heuristic. And yeah, so the results will come out in the paper. Yeah, so that's the bottom line, right? So with compatible exploration time, oblivious auto-tuners are orders of magnitude worse. Okay, so I mentioned added value in the case of tensors. There is also an added value here. We also formalized the type system. And just as an example, and I think this is really a toy example, but what we did is that we added scientific units to the expressions, right? So to the equations. So you could annotate, apart from the type, you can also say, this is in meters or this is in meters per second and whatnot. And so we can actually type check the expressions and see if when you write an equation, that they really type check, right? If you have inches here and in the other one millimeters or something, that there's a warning or the like. And I guess NASA would have liked to have something like this with this Mars mission that got lost. Okay, the third example is a very quick one. So this is something that I'm working in collaboration with the Barkhaus Institute. And the idea here is to raise the level of abstraction and provide kind of a sequential programming interface that looks like Rust for what is otherwise today very complex, moving from a monolithic program into a microservices. So we want to make this manual effort disappear, and that's something that we're working towards. So kind of the idea is to define here our computing fabric is no longer a system, maybe a distributed system, is maybe or maybe not a multi-core, but it's a microservice thing that may run on AWS or Cloud and Heat or different cloud providers. And we want to abstract also from the cloud API, so kind of define a cloud API. And that's a very brief one. So let me kind of switch gears into what we are doing right now with these languages. So what we're doing right now in these languages, for instance, here in the context of this Everest European project that started last year, is that we're looking into using our DSLs for stencils, for tensors, to kind of hook into the WRF model to try and see how can we accelerate some of the kernels. We're looking in particular to the radiation module, connect them with data flow for orchestration, with the data flow thing that I showed you for microservices, perhaps. And we're very interested in advancing this into the MLIR framework, which we're started doing that right in the moment. Okay, so this is something that we're working right now in this collaborative project with people in the Cima Foundation in Italy, working with their test cases on the models and defining interfaces in MLIR to compile to different targets. And in this case, we're just looking into non-emerging, just simply nodes with FPGAs in IBM and Zurich. Okay, let me now switch gears to emerging technologies. So there's a bunch of emerging technologies, as I mentioned at the beginning. Some of the things that we work on are, for instance, hybrid memories, where you have STT and DRAM together in the last level cache. And how can we, because we know more of the semantics of the programmer of the program, we can maybe decide where to put data in the non-volatile section or in the volatile DRAM section. We also work with racetrack memories, and what these are, I'm going to explain in a second. And the other thing that we do, and this is a paper that was recently accepted at the TCAT, is now can we take those abstractions for tensors and generate code for a neuromorphic accelerator using memristive technologies. And this is actually a thing that I'm very excited about, and happy that this paper came out or was accepted maybe a couple of days ago. So these are very interesting things for which I think you really need abstractions, right? It's very difficult to use this accelerator just starting from plain C code or from plain Fortran. Let me focus a little bit on the racetrack memories. For this one, I brought some other examples because I think this is also very exciting technology. What racetrack memories are is now if you look at DRAM, you have an access transistor for a capacitor. You can access a bit through a transistor. And here, what you can do is that here this yellow line here is kind of the access transistor. And instead of accessing one cell, you have access to a magnetic nanowire. And in that nanowire, you can store up to 100 bits. So right now, what it means that you can have 100 times the density of normal technologies. And these are non-volatiles because these are magnetic nanowires. And the way you access data is, for instance, here at the access transistor, if you want to access the bits that are here, and blue is 0 and red is 1, then you have to shift that data down to the access port so that you can access it. So there is a penalty. So you gain in latency. You gain in density. You gain in energy efficiency because this thing is non-volatile compared to DRAM. But you have to do some extra movement of data to be able to access that. So this is something that we started looking into a couple of years ago. Like, how can we map tensor contraction to this kind of memory? How do we play with data allocation? And now again, here, there's a huge value in DSLs because in most languages, you have an assumed data layout. Now we are completely free and we can decide how to map data to addresses. And so what we came up with here by hand first was with an idea of, without going too much into the details, is just to kind of map the rows and the columns. Sometimes just like instead of having this column this way, we would have this column the other way, and the next one like this way, and the other one this way, and this way. So we could zigzag through the data so that we're always shifting only by one. And that's actually that paid off big time. So here you see some results in terms of performance, right? So here you see compared to SRAM, which is kind of really fast, and compared to SRAM after our optimizations, you can get more or less like 25% better performance. So that's not huge, right? But something that I think it's going to be very important, or is very important for us, is not only the P in performance, right? Like the 3 Ps: performance, portability, and productivity, but also energy efficiency. And that's a big gain here in terms of energy on these memories, because as I said, it's non-volatile. So over different tensor sizes, the improved in energy efficiencies by 75%. And here we were using, in these papers, we were using actually quite conservative models for the circuitry and so on. So the gains could even be higher than that. So this was something that we did like per hand, like trying to see how can we map data structures to these weird memories, right? So that we can achieve better performance and also better energy consumption. And so what we did also last year was to generalize those approaches. So we generalized over this thing that we did per hand and see how can we build that into a compiler. And so this is something that we implemented on LLVM using polyhedral methods. And so if we have a polyhedral model that we can abstract from a piece of C code or derive from a DSL, then now we can, on that polyhedral model, we can do transformations that are specific for this kind of memory architectures. And here you see a bunch of results. So lower is better here in terms of shifts, right? So the paper has also results in terms of energy consumption, right? It's more or less 40% less energy. And so you see that for some kernels, it really pays off quite a bit. And here there are some stencils that we borrow from the Cosmo benchmark suite. Okay, so that's all I wanted to tell you today. So let me summarize what I showed you in this I guess almost 40 minutes. Yeah, so I think I want to bring this point through forward, that we need ways to tame this ever-increasing system complexity, right? With these accelerators that are coming up, which I think are quite exciting. There's a lot of relevant work to be done at the level of, say, low-level compilers for mainstream programming models. I showed you some DSL examples, the way, how can we leverage these high-level semantics to improve for efficiency, right? So not only performance, but efficiency. And of course, productivity is kind of an easy thing to see, because you less lines of codes, less complex lines of code. And so at the end, I kind of try to make the connection to these emerging systems, for instance, memory store-based accelerators or new types of memories where you need to play a lot with the memory layout from the compiler point of view. And so I think these high-level semantics are going to be key to target these systems. So moving forward, what are the things that are keeping us busy? The issue of semantic preserved transformation. So I think this is very important. If we raise the level of abstraction, we don't want to break code, right? So you don't want to provide a C compiler and have people debug the assembly code, right? So you don't want that to happen. You want this transformation to be semantic preserving. So as I said, some of the examples that I showed to you, you may say these are just kind of toy languages and so on. So that's why we're trying to see if we can profit from these toy languages in a complex framework like the WRF model is. And so I have a student working on this, like trying to factor things out, and also how to integrate these DSLs and the new compiler into the build system, which is already quite complex. And that's something that we're doing. And as I mentioned, so we are pushing a lot into this MLIR idea of having a reusable set of intermediate languages that people can then use and extend to model the tensors in one side as values, and also to model the emerging technologies, right? Dialects for these new kind of computers that are not necessarily von Neumann. And that's all from my side. So I'd like to thank the members of my group. So there you see some pictures. Also people that work in the group before, that work in these projects, and then collaborators from different areas. Like for instance, this is computational fluid dynamics, this is computational biology, and then other collaborators in compilers and architectures. Thanks a lot.
Okay, thank you very much, Geronimo, for this inspiring talk. So for the audience, you can use the chat as always to ask questions, and they are welcome. We have time to get a few questions. So maybe while some question comes from the audience, I can ask maybe a few from my side. So for instance, I was wondering about the question of dynamic load balancing. I think that's a question that you have when you have a parallel application, and I was wondering how in your approach you could fit this type of instruction or control.
Yeah, that's an excellent question, because dynamic load balancing is something that is dynamic, and so it's not very controllable from the static view of that we have in the compiler, right? Mm-hmm. So I think so I mentioned that in the case of the particle-based simulations, right? So there we were looking into how to optimize for what runs on the node, right? That was our focus. We just used the dynamic load balancer that comes with the library. So that's not my research area. So I guess many people here would know way more than I do on that. So people using the OpenFPN library, they apply those heuristics. That said, one thing that we have been considering is, like, once we do this auto tuning, right? When we are thinking about maybe that's just too academic, but thinking about annotations that you can do on the phenomena that you are modeling, right? So you can give some hints about what you want to do, like from the compiler. So I really like the interaction between compilers and runtime systems, memory controllers, and load balancers. Like what kind of hints we can provide with static knowledge or knowledge provided through annotations so that we kind of ease or restrict the space of optimization that you can do at runtime. But that's not something that we do right now.
Okay, thanks. So far, no question from the audience, but maybe
I see that Petros raised the hand.
He has to use the platform, but maybe Petros.
Can I ask, or
let's go. Yeah, Petros, go ahead.
So thank you for the talk. So one question that I had with this domain-specific languages is when you take them and you compare them, let's say in molecular dynamics. I don't know if you're familiar with a software package called LAMPS. By any chance?
Heard of them? Yeah, heard of them. Yeah, but yeah.
So I mean, I don't know if have you ever compared things or one-to-one with things that are specific to a particular problem, and then try to see whether you can achieve a simulation of a physical system that was not possible before. So in terms of the metric of new science, do you have some examples that you could share? I mean, LAMPS is one. I can tell you other things in vortex dynamics. Could you share one or two examples where this DLS has given new physics?
No, I cannot, and I don't, and that's like far beyond what I'm aiming for, because I mean I'm not the scientist, so I do think, I mean with reduced complexity. So I think in general, right? So this is something that I think is implicit in providing productivity tools, right? So I am a tool guy, right? So with providing productivity tools, I think it is kind of implicit that you foster innovation. But we don't have any concrete example that somebody that took the language and say, oh, okay, now that I can write this, I could write this different models or this different math, and this is more accurate and works better, right? So Ivo Balsarini, with whom I collaborate, so he is interested in new science because he's kind of the collaborator, and he's looking into modeling, I think, what is it, incompressible gels or something. Yeah, so I think I'm hoping that I will get an example from his group. But that goes beyond the innovation that we can do as compiler people, right? Simple compiler people.
Ivo was my PhD student.
I know.
And PPM was a library which is the grandfather of what you're doing. That was.
I know. So the first target of our language was PPM, right? PPM and PPML. Yeah. And so the original motivation to do that was that library was based on like a lot of like Perl and Ruby and different scripts and like putting things together. And so at the beginning, the original motivation was to kind of make a bit more like clean from the software engineering point of view language and avoid those errors that you get some error from Perl or from Ruby when you're compiling.
Okay, thank you.
Okay, so there is a question from the audience. So the challenge with abstraction in generalization, do you have any insight about how this can be done for numeric that don't fit into the usually exercised construct? Yeah,
so the challenge of abstraction, and as I didn't get the first part of the question, but I guess what you're asking is, so there's a common tension between a DSL and the expressiveness that you have in the host in other host languages, right? Where you can write whatever you want. So like in C, you can still embed assembly, and that's kind of a hook that we have in some of the DSLs. So you can still embed other code, but that's something that we want to avoid. And so yet now concretely about, for instance, for the particle-based simulations, so we have a way so that you can define your own differential operator. And that's something that we did in this vortex in cell. But yeah, so for some things you will need some language extension, and I think that's unavoidable. And I think there is a lot of pushback between, so I'm going to be restricted by the DSL. I don't see that as a big showstopper. Is very similar to extending the library as well, right? So in the end, you will require extensions. Then you have to discuss which extension is easier to do, the one in the library or the one in the DSL. I'll say that DSL extension is a bit more difficult to do, but you may gain more things because you have more analyzability and you can do optimizations across library calls.
Okay, and maybe what about standardization? Because I guess if you want adoption of this, you need to have everybody doing the same.
Yeah, that's also not something that I'm right now concerned with. So my main goal is to understand what are the abstractions that we need, right? So for instance, in terms of tensor operators, tensor algebra. To me, the syntax is a bit less, I mean, of course, it's important for the end user, but it's less important, it's less challenging intellectually, right? So the most important thing is, as I was showing, maybe these models, like what is the model that you want to support? Then as a syntax, as I showed you, we can have a syntax that looks like C++ or a syntax that looks like SQL. And so there, that problem of standardization could be solved that way.
Okay, thank you. So far, there's no more question from the audience. We are almost at the end of the session. So if someone has a quick question, you can still take it. Otherwise, looks it's not the case. So maybe then I think we should thank Geronimo for this interesting talk and see maybe at next PASC if everybody has adopted your DSL approach. So thank you very much, Geronimo, for this vision.